People have been asking for a video on pKa, so here goes. You can have two types of molecule. You can have an acidic molecule or a basic molecule. Now, an acidic molecule is one that can give up a hydrogen ion and dissociate into its ion and a hydrogen ion. A basic molecule is one that can accept a hydrogen ion and become a positively charged ion. Acidic, basic. Now, the interesting thing is, if you take an acidic molecule and put it in an alkaline environment, that will encourage it to dissociate. And the opposite is also true. If you take a basic molecule and put it in an acidic environment, then it's more likely to accept a hydrogen ion and therefore ionize. It makes sense, therefore, if you take an acidic molecule and put it in a slightly less acidic environment or a slightly more alkaline environment, a few of those molecules are going to dissociate. But if you put it in a really alkaline, shove it in bleach, a really alkaline environment, then all of those molecules are going to dissociate. There's a scale of how many of those molecules have dissociated or have ionized. And the same is true if you take your basic molecule and put it in a slightly less basic, slightly more acidic environment, a few of those molecules will take up a hydrogen ion and ionize. And if you put it into hydrochloric acid, all of those molecules will accept an H+, all of them will ionize. You've got a scale of how many molecules have ionized. That's where pKa comes in. pKa is the point on that scale, the pH value at which half of your molecules have ionized. And that's for an acidic molecule or a basic molecule. It's still a pH value either way. So if you've got an acidic molecule with a pKa of 7, it means at a pH of 7, half of those molecules have ionized, have given up an H+ ion and are now in their ionized state. If you've got an alkaline molecule, a basic molecule, and it's got a pKa of 7, it means at a pH of 7, half of those molecules have accepted an H+ ion and are now in their ionized state. So why does this matter? Because unionized molecules are very good at crossing cell membranes. Ionized molecules are terrible at crossing cell membranes. And we as anaesthetists are really interested in neurons, either brain cells, spinal cord cells, or peripheral nerves. And all of them are surrounded by cell membranes and fatty tissue, whether it's white matter in the brain or a myelin sheath in a peripheral nerve. We want molecules that can get through fatty tissue and through fatty lipid cell membranes into the neuron. And polar molecules can't do that very well at all. So we want drugs that are acting on the neurons to be in their unionized state if they're going to work. And the classic example of this is if you take lidocaine and inject it into infected tissue, it doesn't work very well at all. The reason it doesn't work is because of the pKa. Lidocaine, it's a basic compound, and its pKa is 7.9. This means that at a pH of 7.9, 50% of the lidocaine molecules are in their ionized state and pretty useless because they can't cross into the neuron, they can't do their job. So that's at a pH of 7.9. If we bring the pH even lower from 7.9 down to 7.4, which is normal body pH, even more of those molecules will be ionized. We've got even fewer non-polar or non-ionized molecules that can get into the neuron. Now, infected tissue is even more acidic. It could be down to pH of 6.7, 6.8. So even more lidocaine molecules are going to be in their useless ionized state. That's why it doesn't work. It's there. They can't cross the cell membrane. It can't get into the neuron. So that's pKa. It is literally the pH value at which that molecule is 50% in its ionized state. And it gives you an idea of how well your molecule is going to work or how quickly it's going to work at a given pH. And an alkaline environment will make an acidic molecule ionize, and an acidic environment will make an alkaline molecule or a basic molecule ionize. And in general, in anesthesia, we want molecules in their unionized state.